Hugo.
Yes.
No. Okay. Sorry. Hugo will first talk about the generic. I think we forgot that. Hugo was supposed to come next. Okay.
Yeah.
Hugo will talk about the state of the art of gas turbine engines. Okay. All right. Yeah, I'll open it. That's all right. Very good. Slideshow. Beginning. And you need this.
You're under control here, right? Okay. Well, let me briefly introduce myself again. I'm Hugo Pförtner. I'm from MTU Aero Engines, and I'm with MTU Aero Engines for 27 years now. And my main focus of work during that time was designing and introducing monitoring systems for military engines, for fighter engines, but also for helicopter engines. My current work is in designing new systems for fighter helicopter, for the French, German Tiger helicopter, and I'm also working a little bit in analyzing the data from the A400M. Okay. Yeah. Okay. As mentioned before, building new sensors, new actuators is not something that's for its own, but it has to fit into the global targets we have for our engines. And the global targets, of course, are performance here, performance for the military. They want a lot of thrust at low weight and low size. And the military also goes for mission readiness. That means they want their aircraft, their fighter plane, their helicopter available whenever they need it. And they want to predict that it is mission ready. Of course, then another thing is now more than ever is affordability. That means nobody now is willing to pay an arbitrary amount of money to getting a new capability, and for the military, acquisition cost is one of the big drivers. It's a little bit different for civil. There is fuel burn and so, but then operating cost, of course. Then also one of the military requirements is a small logistic or manageable logistic footprint. That means you don't want to deploy a helicopter to a foreign country and then send 500 persons of repair and maintenance stuff along. Of course, in civil applications, this more the military part, that's the civil part here. We want safety as paramount for everything. Yeah, that means we won't have accidents. Even if the rate is very low, we still have the requirement to go down with any accident rate. We want to be fuel efficient. That means to transport a passenger from Europe to the States or to Eastern Asia. We want to do it at low cost and at low fuel burn. And of course now we have this environmental impact, which is emissions now, which is noise, and for the military, of course, also the detectability. There's a vision that's here for the Advisory Council of Aeronautical Research in Europe. There had been very similar requirements also in the US and elsewhere in the world. And as basically you see the same things I already mentioned. You have here in safety and security, we want to reduce the accident rate by 80%. We don't want to have hijacks of aircraft. Also, that is a thing that's of interest. We want to have new technology in a reasonable time in the market. That means nobody now goes for 10 or 15 years of development. We want to have an idea and we want to have it in the market in 5 or 6 years and not in 10 years. Of course, everybody expects that travel will remain to be affordable, to be cheap even. Yeah, you know, all the everybody goes for this low price ticket. Then, of course, whenever you travel with the airplane, you don't want to sit around at the airport unexpectedly for 2 hours. So you want that all the arrival times and departure times are as scheduled. And since aircraft and engines, everything is expensive, you want to use this aircraft to a maximum amount. Yeah? Typically in civil transport, in short term, you have 4 or 5 or 6 flight legs a day. Yeah? So, oh, sorry. And which is now one of the big concerns is the environmental impact. We want to reduce the NOx's by 80%. We want to reduce CO2, which is mainly achieved by low fuel burn. And current targets from the engine are, we think with engine technology, we can have a reduced fuel consumptions of about 50 to 20%. We can reduce NOx by 60 to 80%. We want a reduction in noise by a factor of 2, which is 10 dB. We want to reduce the accident rate. We want to reduce operational costs, and we want to have it in near future. Well, a little bit, a few numbers on the current status of civil air traffic. Aviation contributes 2% of carbon dioxide emissions. That's not a big figure, but it's one where we have an influence on. Yeah? You don't have an influence on the CO2 that's produced by the rainforest or so, yeah, if it's there. We have 2 billion passengers per year, and currently 1 passenger kilometer leads to an emission of 50 to 75 grams of carbon dioxide. And we have already had a big reduction during the last 50 years. So if we compare it against the technology of the 1960s, we already have a 70% reduction, and this is now widely ignored. Everybody's talking as we are starting from scratch and from new. We already are at a very high level of technology, and we are starting now having this large reduction, and we want another 25, 50 or whatever percent on top of it. Yeah? And the main contributor, of course, was the change in engine architecture. For the civil transport engines, we now have the high bypass ratio engines, and also the cycle pressure increase. We've gone up to pressure ratios 40 or something like that. Yeah? And that had been the main sources of efficiency improvement. This is a chart from a technology program in Europe, which I show later. It's the engine core technology program. And this is the target. Currently, we have as reference an engine that has a bypass ratio of 5 to 8, like the Trent 7000 or the CFM 56. And that is the way where we are currently going. And now the current engines that go into service now, the one for the 787 Boeing, have this reduction by 10 or 12%, but we want to go further down to this 20% target, and by just following this path here, we come into something like a saturation. I will talk about it. What are the main limitations of going still to higher bypass ratio, going to higher temperatures, going to higher pressure ratios of the core? We simply need something new. We have to go to, we have to leave the conventional turbofan and have to find new concepts. This is something that's, of course, the military. There is not too much military new development in Europe currently, but there are several programs still ongoing, also not widely made public in the United States, but that are is the main focus if you develop it. The main focus if you go for a new military engine, of course you want this availability. It's gone? Sorry. Okay, I use my finger there. Doesn't work. You want no component failures. You want to have the available life really of your engine. Military engines, the next generation might have to last for 50 years. Yeah? So it's really important that you can use the life of your components. Your maintenance friendliness is a big driver in military engines, and also the small logistic footprint. And one thing that's different in military engines, they typically have to be integrated into the vehicle, and that's difficult because for observability reasons you have complicated inlets, you have exhausts that are expected to reduce your IR signature, and you have everything inside the aircraft, and the future aircraft might be an unmanned one. So you pack a lot of electronics in it, and where to go with your heat. Yeah. Well, future military engine might look quite different from what we see now. That's artist's impression, I think, but the real one is not too different from it. What is currently being researched in the United States. You see there's quite a complicated shaped inlet just to hide the inlet from radar. And this core region is also more complicated than we have in current engines, because they want to divert the flow dependent on the flight regime. That means you both want high efficiency when the aircraft is on cruise, and you want high efficiency or maximum thrust when the aircraft is on attack. That means you have to do some macroscopic flow switching in this engine. Will have very high bypass ratio, and it will have active elements in the inlet and perhaps also in the exhaust to improve stability and avoid flow separation.